Good afternoon, everyone. Thank you for coming. Today we have a great guest. We have Sebastian here that came from Oxford. Some of you already communicate with him. Sebastian did his undergrad studies in Colombia, and then he worked 6 months in CERN. And then he started his master in Cambridge University, and then moved to Oxford. So he's really checked all the high quality university in the world, and now we came to UNSW to compare our facilities. Sebastian worked on surface passivation, and from the email communication that we had, it seems like he's very knowledgeable in all this area. So I'm quite sure that we will have great talk with him. He will stay here for another 2.5 weeks or 2 weeks?
2 weeks more.
2 weeks more, so you will have the pleasure to speak and ask more questions. So please welcome Sebastian to UNSW and for this seminar.
Thank you, Sif. Thank you. Thank you, Sif. Thank you. I'll just start quickly on the matter of comparison. This level of sophistication does not happen at Oxford or Cambridge, so just so you know. I'll also briefly thank Ali for arranging all of this trip. Despite not being here, I'd also like to thank Phil Hamer and Brett Hallam, because they've been sort of instrumental in building up a incredible collaboration that we now have between Oxford and UNSW, so that's great. Okay, now onto my talk. So today I'm going to talk about extrinsic surface passivation for silicon solar cells. And this sort of word extrinsic is kind of the main thing that I want to refer to over and over again, because it's sort of a concept that we've tried to start getting across to explain certain things that have to do with surface passivation. So here's the context. I'm going to start with some surface recombination basics, just to get everyone to the same sort of level of understanding. Then I want to talk about 5 important things. The first 2 will be fairly short. One is a few key aspects on a dielectric silicon interface that I think are normally not very well understood. Then I'll talk about recombination metrics at the surface, which is something else that is only recently become an important topic. And then I'm going to go into the main part of the talk, which is this difference between intrinsic and extrinsic passivation methods for the surface of silicon. I'll talk about the potential of the main topic that I work on, which is charge-assisted field effect passivation. And then I'll touch briefly on point 5 there, which is the work of my colleagues at Oxford, which has to do with hydrogen in silicon and how to introduce hydrogen without any damage. Right, so let's start. So here we have a typical solar cell. So actually I'm supposed to be using my mouse. Let's see whether that works. Yep, good. So here we have a typical solar cell. We have a injection of carriers. We have our quasi-Fermi levels. Here's a energy diagram. We have a concentration of electrons, a concentration of holes, and then we have some defects in the band gap, some bulk defects and some surface defects, right? Here schematically we have the concentrations of holes and electrons as a function of distance in that solar cell, and we have a term that describes what the recombination looks like in that solar cell as a function of how many defects we have. So if now we focus on the surface of that cell, here we have a semi-continuum of states by which a electron-hole pair can recombine. And so here I'm going to make reference to the 2 typical things that are talked about when one understands surface passivation. So the first thing that we do when we surface passivate a silicon, it's we put in a dielectric coating, and when we do that, we eliminate a number of those states, right? So that reduces the amount of recombination that takes place. So just in general terms, we can see that this big equation here is more or less proportional to the number of states that we have times the minority carrier that is available there for a recombination process. And so the first thing that we've done is reduce that term, that NT there. And the second thing that we can do is reduce the number of available carriers for a recombination process. And we do that by establishing a concentration of charge in our dielectric coating. And so that bends the bands further, right? And it really changes the concentration of electrons and holes that we have at the very surface. And by doing that, we can minimize the recombination process that takes place at the surface. So this is more or less what's understood as the chemical and the field effect components of passivation, right? So this is what most publications and most understanding talks about. So these two components. And what I want to get across is two additional components that I normally ignore, but I think are equally important when understanding what happens to the surface in terms of carrier dynamics. And so these two other aspects is first the nature of those interface states that we have between the dielectric and the silicon. And the second is the ability of those states to capture electron-hole pairs. So let's go on to the first one. Here again we have a schematic diagram of a silicon surface. It's passivated with some dielectric. We have our energy band diagram, a generation of electron-hole pairs. Here we have a concentration of electrons, a concentration of holes. Then we allow a number of states to be at the surface of our silicon. And the key thing here is that some of those states are actually acceptor type and some of those states are actually donor type. And so some of those states will naturally have certain type of charge and will become charged when something happens. So in acceptor states, we will have negative charge when they get occupied, and in donor type states, we will have positive charge when they're emptied. So in this example here, for instance, if we have those Fermi levels as they're pictured there, what we know is that there will be some concentration of those states will be occupied of the acceptor type, so they will be negatively charged. And to compensate for that negative charge, we normally have a small space charge region at the surface of our silicon, which this is a very normal phenomenon. Right. So then, when we go and try to passivate this using field effect, using charge in the dielectric coating, the first thing that happens as we put charge in that dielectric coating is that some of that charge gets compensated not only as a space charge region, but also as charge in those interface states. So here I've schematically put, say, 5 charges there, and we see 3 of those charges are actually compensated in the interface states, while only 2 are compensated as space charge region. And it's important to remember that when we are reducing the recombination rate, we want to reduce the number of carriers at the surface. In this case, we want to reduce holes at the surface, and these holes are the concentration there and there. So what actually happens is that when we have a concentration of the charge of the dielectric being mirrored as charge in the interface states, that makes field effect passivation less effective, right? So depending on what type of charge is being mirrored in these interface states, we would have field effect or charge-assisted passivation, which is more or less effective. And this is a key component on how we understand how we passivate silicon surfaces. So that's one thing that I wanted to make clear. Then the second thing that I want to make clear is that to do with the ability of a interface state to capture an electron-hole pair. So in most studies, one makes reference to the DIT, or the concentration of interface states in the silicon surface. Now, while that is important, the recombination rate is actually proportional both to the concentration of those states times their capture cross-section. The capture cross-section times the thermal velocity is a capture rate, and that capture rate tells us how that state is good at recombining, how able is that state at recombining electron-hole pairs. So it is actually the product, or those two things, what really matters. So if now we go on to how this is a recombination rate on a single state, if we now sort of expand that concept to the surface of silicon, then we convert that into a surface recombination velocity. And here we have, instead of having a single energy density of states, we can have a semi-continuum, and we normally group that up in the SN0 and SP0 values, which are dependent on DIT, which are these values here. And so the thing that I want to get across here is the fact that when we passivate chemically a silicon surface, is not only about reducing the number of interface states that we have, but also reducing the ability that those states have at recombining electron-hole pairs, right? And I'm going to give one example later in the talk about how this sort of became important in one of the studies that we did. So keep that in mind. Right, so the next thing, point number 2 in my agenda, was surface recombination metrics. So there was this really nice study by Keith McIntosh and Lachlan Black, where they looked at these two recombination metrics, so surface recombination velocity and dark saturation current density. And by looking at some approximations, they could see that actually the recombination velocity and the saturation current density would have certain dependencies, both on the number of carriers that we have at the surface, but also the bulk concentration of the silicon that we have. So, for instance, in the first two cases, if we have dielectric coatings that have very little charge concentration, we would have surface recombination velocity as a very good metric, because this is not dependent on the dopant concentration of our silicon, which is in this parameter ND here. Whereas if we have dielectric coatings that have very large concentration of charge, then the surface recombination velocity then becomes dependent on that bulk dopant concentration, whereas the J0 value then becomes independent of the bulk concentration, right? All of this just to say that whenever a recombination metric is used, it should be accompanied by what is the material that you're analyzing this on. So if it's N or P type, and what level of dopants you have, right? So I'm going to try to keep to surface recombination velocity, but in all cases, I'm going to quote what bulk material I'm using to try to keep it as complete as possible. So this is one of the points that I want to make clear. Okay, so now let's move on to this difference that we're trying to make between intrinsic and extrinsic passivation. So here we have again a N-type silicon surface. In this case, I've used a simulation of a single mid-gap defect. So the recombination velocity is given by this term here. I've let a charge at the interface of 10 to the 11, just simplify a little bit to have a easy number of plots here. This is done on an N-type silicon 501 centimeter. So we have our N-type silicon number of states there. The first thing that we do is we deposit a dielectric coating on top. That dielectric coating, so we start at a recombination level somewhere around there. We deposit our dielectric coating. That dielectric coating takes away some of the interface states, and it also produces a concentration of charge. And what that does is it lowers the recombination rate, but it also moves on the x-axis here we have dielectric charge concentration. So we've not only reduced the chemical passivation, but we also produce some concentration of dielectric charge, which further reduce the recombination velocity at that surface. Now, the next thing that we can do is we can do processes that happen after the dielectric coating is being deposited. So this is what now we understand as extrinsic surface passivation. And the first thing that we can do that is very well known in the literature is that we can introduce hydrogen to those defect states, right? And that hydrogen is believed to passivate some of those defect states, such that it prevents them from having any recombination activity. So then what that does is it takes our recombination velocity farther down vertically, because that's only of the chemical type. But then the other thing that we can do is we can produce a concentration of positive charge in that dielectric externally. So after the dielectric coating is already there, we deposit some positive charge, and what that does is it further reduces the recombination rate that we have. So here I'm trying to exemplify the fact that by combining both the chemical passivation, so the reduction in the recombination activity of those defects at the interface between silicon and a dielectric, and by producing a concentration of positive charge or any charge type at in that dielectric, we have those two things combined to produce the best possible recombination velocity that we have. So very, very low recombination. So here's basically what I've just said. Charge is actually very, very, very important for the surface passivation. In terms of intrinsic passivation, the intrinsic passivation gain only after we deposit our dielectric coating is somewhat limited, because whenever you grow or you deposit a passivation coating, you have to optimize both components, the chemical and the field effect. And if that dielectric coating also works as an anti-reflection coating, then the optical properties of the dielectric also have to be taken into account in a single process. Whereas if we use extrinsic as a method to passivate, then that allows certain level of independency in how we take that into account. And here I changed the recombination rate, or the sort of generally spoken belief that it's chemical passivation is only relates to DIT, to the fact that it actually relates to the product of DIT times the ability for those states to produce recombination. So, so we studied this, and we sort of understood that this could be done. So then we went on to try how this would actually affect the passivation at an interface. So to do this, what we did is we took a piece of 1 ohm centimeter N-type silicon. We grew a 100 nanometer silicon oxide dry, and then we deposited a concentration of positive corona charge on both faces of that dielectric, measure Sinton lifetime, and this is what we got. So if we start from around there with negligible charge concentration in the dielectric, we have effective lifetimes of around 100 microseconds. And what we saw is that as we deposit positive corona charge on that dielectric coating, we could get effective lifetimes at a 10 to the 15 exceeding 3 milliseconds. So that's actually an enormous increase in the passivation quality of that film. The other thing that we tested is that if actually before doing the corona deposition of charge, we forming gas anneal that same film to introduce some hydrogen and improve the chemical passivation. So we would start with an effective lifetime, maybe slightly better, maybe 200 microseconds at 10 to the 15. And this time when we charged it, we could get all the way up to about 5 millisecond effective lifetimes, which are now getting for some of the best. Just for comparison, here is the intrinsic limit of that piece of silicon that we're using there. Here, most of you would have seen this split between different components of lifetime. In this case, we calculated the recombination velocity. For the case that doesn't have a forming gas anneal, this is equivalent to about 1.4 centimeter per second, which for those who are familiar with recombination metrics, in terms of surface recombination velocity, this is fairly good. And I'll later show how this compares to other work in the field. So we saw that actually this was a very nice proof of concept. So this demonstrated that actually you could extrinsically use a method that would provide a concentration of charge to our dielectric coating, and it would improve the passivation quite strongly. So we did this in all cases N-type silicon 1 centimeter, first with silicon dioxide. We also did it with a forming gas anneal, 4% or so hydrogen anneal. This produced recombination velocity of 0.6. And we also did it with a different method of hydrogen passivation, which is the one that I'm going to discuss at the end. And these lower the recombination velocity even further to 0.17 centimeter per second. We also tested it in different dielectric stacks. So here is a double layer oxide nitride. We know, and most of you would know, that silicon nitride, when you deposit it using ammonia in a plasma chamber, that liberates a large concentration of hydrogen, and that hydrogen tends to go and passivate a lot of the interface states. So that also helps. Here we have again a lower recombination velocity, 0.15. We've done it with silicon oxide and amorphous titanium, recombination velocity of 1.2. And then lastly, we did it on a triple layer of amorphous silicon oxide, silicon nitride, and this has produced pretty well the best recombination velocity that we've ever measured in N-type 1 centimeter silicon, which is 0.01 centimeter per second. So this measurement is a little difficult to estimate, and I'll show you in a minute why. So we've done this across a number of dielectric coatings, and it's actually turned out to work really well despite the dielectric coating that you use. Now I want to look at this example of the triple layer, amorphous silicon, silicon oxide, silicon nitride. Here we have the effective lifetime curves. First, when you deposit the oxide layer, the effective lifetime is not very good. But once you deposit the silicon nitride layer, which is the empty blue symbols here, your effective lifetime goes up again. But when you deposit the corona on top of that, to basically optimize how much field effect passivation you can get out of this stack, you get a effective lifetime of these blue points here, and actually maybe at 2 or 3, 10 to the 15, it goes above the intrinsic limit of Auger recombination parameterized by Richter. So this is one of, I think, only 3 studies where a effective lifetime in silicon is being measured above the intrinsic limit of Auger. So this is now basically suggesting that parameterization is invalid. So probably we have higher bulk lifetimes that we think. The next thing we did is we took that sample and we used capacitance, conductance, voltage measurements. So here is a typical spectrum measurements of that structure. The top one is amorphous silicon oxide only, and the bottom one is when we include the silicon nitride. And by doing that, we can construct a picture what the DIT looks like at our interface. And here we can see that at the beginning we didn't believe these measurements too much because this is actually quite high values, and I'll show a comparison in a minute. This is about 3 or 4 times 10 to the 11 in the case of the amorphous silicon oxide and nitride, which is actually quite high given the fact that we got just about the best recombination velocity that we've ever observed on that material. Here we remember that actually the recombination rate is dependent both on the DIT and the ability of those states to capture electron-hole pairs. And this is what I want to make an example of today, and is the fact that this DIT, at least in every measurement that we took, so here actually there is an example of 3 different measurements, and we measure a few more, and in all cases we saw that actually that was a correct measurement. The DIT was indeed above 10 to the 11, which is quite high. So if that is the case, then the only thing that can explain why you have such low recombination velocity, which gives you extremely high effective lifetimes, is the fact that the capture cross-section for those states has to be really very small. So this is something that maybe before wasn't so important or so taken into account, and here we see that actually it's a key factor. So if we put that in the context of this very nice graph that Andres Cuevas presented 2 years ago at one of the IEEE meetings, so we can see that what used to be known about amorphous silicon is in the order of 10 to the 10 to the 11, right? So down here. We believe that it's actually higher up, and that a more accurate label for this y-axis here is the SN0 or SP0 that describe the full chemical component of recombination at their interface. So that's one thing that I want to say here. The other thing is that these arrows here describe how to get better surface passivation. And the key thing that extrinsic methods allow you to do is take all of those curves, all of those circles of where the passivation lies after deposition, so all of the intrinsic terms, and move them to whatever you want. Right? So you can virtually change, if you take any of these coatings and you put more hydrogen into it, you could be pushing all of these down, or if you tailor the charge concentration, you could be moving them towards more charge, positive charge and more negative charge in that dielectric. So that's actually a very versatile methodology to do what you want with your coatings. Here I've put a chart of the state of the art, at least 2 or 3 years ago, of surface passivation. So here on the left there is the surface recombination velocity. We have the first bar is the Al-Nil, which is a very well-known process that produces recombination velocity somewhere between 1 and 2. And here is a number of different techniques. Then PECVD silicon nitride became very good. Then there was the development of ALD aluminum oxide, which produced some of the lowest ones. And here the last 3 is the work that we've done on silicon dioxide. And here we can see that actually those surface recombination velocities, as compared to all of the other major techniques to passivate a silicon surface, is actually pretty very good, especially in the case of an oxide nitride layer. We also recently worked with Bram to produce a good review of what has happened in the past 10 or 15 years in terms of surface passivation. And here you can see the evolution between 2002. So this work here is Karen Cuevas and Schmidt working on oxide and nitrides. And what we can see is that throughout those years, we've managed to reduce the surface recombination velocity by quite maybe about an order of magnitude or even a bit more. And we're very happy that in Oxford we can claim those 3 points last there were all done at Oxford. So we're very happy about that. And also it makes you wonder whether there's any further improvements that you can actually make, because at this point I mean, once you measure a lifetime that is above the current intrinsic limit, then there is not really much else you can do in terms of surface passivation. So it also appears like we're getting to the point that it's very difficult to improve passivation from there. Okay, so I've told you about extrinsic passivation. You know that now that we tested the concept, it works pretty well. It also works independently of chemical passivation or of the optical properties of our dielectric coating, but how important it is for a solar cell. So here's just one quick slide on what it means in terms of the efficiency of an IBC cell. And I only make reference to an IBC cell because that's how we started this work. We sort of point towards what was the cell architecture that was most sensitive to front surface passivation, and we thought, okay, so let's try and do the best of an IBC cell. Here we have the typical geometry of an IBC cell, and here we have how the efficiency varies with the front dark saturation current density. And we have, in the inset, we have how the dark saturation current density varies as a function of charging that dielectric, both when we have the presence or the absence of a front surface field. So a front surface field is a very common thing to put on the front of that cell to improve surface passivation. So two interesting things here. One is that if we don't have the front surface field, so the purple trace here, we can actually achieve better J0 or surface recombination velocity values, and that's because we don't have the added Auger component of recombination in that heavily doped region at the front. And the other is that if we look at the performance of that cell, if we have J0 values below 10, we actually have very little variation of the performance parameters with recombination velocity at the front surface. But once that goes above, say, 20 or 30, then the performance of that cell actually quite rapidly decreases with the quality of your front surface passivation. So that's an important part to consider there. So that's just to put it in the context of how important it is for a solar cell. Right. So the next question that everybody asks about this is whether that charge is stable or not. And most people who have worked with corona charge will know that actually corona charge is highly non-stable and is especially dependent on your environmental conditions. So if you have a very humid environment, it will tend to decay quite quickly. So we tested that, and we saw that actually our corona discharge decayed in a matter of days, maybe 10, 20 days. And so we proposed a new way by which we can introduce the charge, and this is the other main part of our work. So in this methodology, what we do is instead of having corona ions at the surface of our dielectric coatings, we have big charged ions that we embed inside the dielectric coating at high temperature, such that once the whole structure is quenched, the ions are effectively frozen in that dielectric. So how we tested that? We put in a concentration of species at the surface of our coating, and then we held that at high temperature. So here we did anneals at 400, and our precursor species were actually potassium chloride. So we chose potassium because we know from the semiconductor industry that alkali ions have the tendency to diffuse very fast inside silicon dioxide. And so this would be a very good way of testing this as a concept. So here we did the deposition of potassium chloride, anneals at high temperature, and what we saw is that actually those positively charged potassium ions do diffuse in and do provide some level of surface passivation, increasing the effective lifetime up to about 700-800 microseconds in that sample. Now this took about 100 minutes, which is not particularly a fast technique, so not necessarily something that would be very commercial. So the next thing is that we thought, okay, how can we do this faster? So as in most diffusion processes, the next thing that you can think of whenever you have a charged particle is you can not only allow concentration gradient diffusion, but you can also allow drift of the particles, right? And all you need to do is you need to overimpose a electric field. So to do that, we deposit a concentration after doing the species deposition. We corona charge the film such that the corona charge would impose an electric field pointed towards the silicon, and that electric field would push the ions into our dielectric coating. So we did that. Unfortunately, when you do samples with and without any potassium ions, they show absolutely no difference. So here we have the starting lifetimes we corona charge them, we know that the lifetimes go high up, then we anneal them, the lifetime decrease a little bit, but not too much, and then they're virtually the same regardless of whether you have potassium ions or not. So that test wasn't too good. But then what we did is we took that exact same sample and we monitored it over 4 years in standard lab conditions. And what we saw is that in the case that we had potassium ion in the oxide films, we would have really good surface passivation all throughout the measurement period up to about 4 years. So here we measured the effective lifetime, and in all specimens having potassium ions, we saw a really good stability, whereas in those samples that were controls and didn't have any potassium ions, the effective lifetime actually decreased quite low, showing that no further surface passivation had been provided. This is in the case of drift and diffusion, and if we only diffuse the samples, of course it would have taken us over 100 minutes, but in all cases, and when we did it at different temperatures, they all showed a very small decay rate. Here we also measured it to about 4 years, and in some of the best cases we have samples with still above 700 microsecond effective lifetimes. So this is maybe a recombination velocity of about 10 centimeters per second. Just to double check what we were doing, we also measured the charge concentration. So we did Kelvin probe and we did flat band voltage measurements in CV. And we can see that the samples that did have potassium ions, so these blue and yellow, do show the concentration, the shift in the flat band voltage, indicating that the charge concentration is there. In this case, I think we only did it for about 500 days. But that's still pretty good indication that the charge is sustained in the dielectric coating, at least in that lab conditions. We characterize all of this using a decay time constant, so simply fitting a single exponential decay curve. And we could see that in all cases, we had really good decay time constants. When we did diffusion over 550 degrees C or diffusion plus drift at 400 degrees C, we could see that our decay time constant is now exceeding 10,000 days. And in the best case, I think, is the drift and diffusion at 400, which actually only took about 2 minutes. And the decay time constant is about 17,000 days. So this is the equivalent of a decay in about 30%, 30-something% in about 40 or 45 years, right? So now this is looking more like a technique that could be used industrially. Okay, so just to summarize this part, we've made a pretty good progress towards a method that could be industrially used to extrinsically passivate a silicon surface. We're still working on how to get the right combination of ion in diffusion, the times, and the stability. But so far, the results are very, very positive. Okay, so I'm going to finish with a few slides on extrinsic hydrogen passivation. So this is work that mainly has been done by my colleagues Phil Hamer and Gabrielle Bourret. So many of you would have known Gabby. She was here for a little while. And here, the key part is that so far, there have been mainly two methods of introducing hydrogen in silicon. One of them is doing forming gas anneals, but that's not necessarily the most industrial thing. It's relatively expensive. And the other method is having dielectric coatings that have a large concentration of hydrogen in them, and you can tailor how they release that hydrogen at high temperature to embed the hydrogen into our silicon underneath. So we wanted to come up with a method by which you didn't need to do either of those things. And what we came up with was having a hydrogen plasma in a standard direct PECVD machine, but having that hydrogen plasma isolated from our sample, because what was known from before is that whenever you have a plasma, there is high risk for damaging your sample due to high energy radiation, ion bombardment, high electric fields, and so on. And so what we did is we came up with a shield that you could put in your PECVD chamber just on top of your sample, and you could have a membrane that is completely opaque to high energy radiation that could absorb all of the ion bombardment, but that could be permeable to hydrogen ions. And so we tested this, and the first test we did it with a palladium leaf, and this palladium leaf is known from other industries to be a standard material for purification of hydrogen because it's very, very permeable to hydrogen and not to many other things. So using this, we proved that actually we could produce some hydrogenation of silicon that was damage-free from the plasma. We did, to test that we actually had some hydrogen in our structures, we did ECV of very heavily boron-doped samples, and we can see that we could passivate or inactive, or cancel the electrical activity of boron near the surface, and we could vary this as a function of time. But we could also test it on oxide passivated samples. So this would simply introduce some hydrogen into the interface of thin oxide films on silicon, and we could see that whenever we did that, we would get better J0 values on our specimens. We also tested the conditions of our palladium leaf, palladium foil, and we found that actually you could do quite a few things to try and change the kinetics of the hydrogen ions at the surfaces of that palladium leaf. So you could poison the film, so basically you can introduce additional other ions into the palladium, and this would serve to avoid certain reactions taking place. And the key reaction in when you want to hydrogen passivate is you want to avoid monatomic hydrogen recombining into molecular hydrogen. And that was the one thing that we observed was pretty key. We've also tested both palladium and palladium silver foil, and the palladium silver foil is simply from the point of view of certain phase changes that happen at high temperature in palladium. So we also wanted to avoid that. And here is the measurement of one of those recombination velocities that I talked about. So here we have a hydrogen passivate sample using this methodology and an effective lifetime of almost 6 milliseconds when you add corona discharge to this oxide. So this is once again some of the best recombination velocities that we've observed. Just looking towards the future, this is something we haven't done, but we've checked that actually it is possible. There is no fundamental reason why you couldn't have a plasma in a low vacuum system and then your samples just flowing underneath and having a mean-free path sufficiently small between the shield and the place where your samples are, such that they could get sufficient hydrogenation in a inline looking like system. Yep. Okay, so just to summarize, I've told you a little bit about the understanding of the dielectric surface, dielectric silicon interface, and the things that we've sort of understood over the past few years. I've shown you that doing this comparison of this difference between the intrinsic and the extrinsic components of surface passivation, we can actually exploit the extrinsic surface passivation by doing different methodologies, different processing to our films after they've been deposited. And this led to surface recombination velocities below 0.1 centimeter per second, which are some of the best that have been observed. And we've also done some progress towards stable and fast, towards getting this methodology of extrinsically passivating silicon using big charge ions to a fast and sort of commercial system. I'll acknowledge Fraunhofer, UNSW, of course, and the University of Central Florida, who have been working with us. And I'll finish with this, which is just a plug for a special issue that Bram and I are co-editing on surface passivation, just to try and get together all of the progress that we've done there. Thank you very much.
Any questions?
I've got 3 questions. Just start with the paper you referenced from McIntosh and Black. In your opinion, do you think J0's a better metric then for these charged films?
Okay, so in my opinion, yes, because that's the way to put it. In my opinion, I think all metrics should be actually quoted. I don't prefer J0 to SRV, for instance, but I think as far as whenever possible, people should quote all of them.
I mean, in that paper, they give guidelines as to which metric you should give under certain conditions. Yeah. So, if you follow the conditions that they suggest are the best, then whenever you have a heavily charged dielectric, then
you use the J naught, and whenever you don't have a heavily charged electron, you use surface recombination velocity. But having said that, I think there may be occasions where that doesn't hold. And I guess just from personal opinion, I think having both metrics side by side is probably the best thing that you can do. So in that review paper that we wrote with Bram, the decision was actually, let's have all of the metrics one next to the other, because that way you can actually see how all dielectric coatings perform both on, say, SRV, J naught, and VOC, for instance. So in my personal opinion, I think people should quote all of them, because it's very misleading to have just one of them. The other thing that, for instance, I did mention is the recombination is a lot easier to passivate lightly doped material, so high resistive material, and that's something that is not very common, or not obviously said. So people come up with, I don't know, 30 or 50 millisecond lifetimes, and recombination velocity is near 1, and the surface passivation is not necessarily good. It's just a lot easier structure to passivate. So in all possibilities, not only having the two metrics, but on what kind of material you're doing this, actually tells you the whole picture.
Okay, next question. Your amorphous oxide nitride stack, do you have any insights as to where your charge is sitting in that case?
Yes. We think the charge sits at the interface between the oxide and the nitride. We're fairly confident of that. We didn't quite measure it, but so there is a measurement, fairly easy measurement that we do is we deposit the charge, and then we measure the Kelvin probe surface potential. And what we can see is that the charge, the value of surface potential that we get starts going down quite quickly, but it doesn't go down to 0. So maybe it goes down by a bit, but then it stays at a certain level. And that seems to indicate that all the charge goes on the top and then migrates towards the interface between the nitride and the oxide, and then stays there. So if you combine that with the fact that the effective lifetime didn't decay, then it's a pretty good indication that the charge sits at the interface between the two.
Yeah, I'll leave it at that. Thank you.
Cheers. Alison?
A question about the charged, the ion charged dielectrics. Have you thought about testing them under high voltage? I mean, the reason I ask is, there's been a lot of reports looking at PID and the being due to sodium from the sodium ion glass, or the glass actually permeating in through the dielectric and going into the silicon. Is this something you've looked at?
It's something we haven't looked at, but we are aware of it happening. Now, I guess the straight point about that is the fact that PID is somewhat solved already, and the solution in most cases involves depositing a very thin, highly conductive for a dielectric layer as the outermost layer on a dielectric stack. And all that does is it prevents from a high electric field falling between the top of your dielectric coating and the interface to silicon, which is where the ions would sit. So in that sense, we were not very worried about PID being something that could damage the passivation provided by ions. But the expectation is, of course, if you had a very strong electric field, once you elevate the temperature probably above 100, 150, a strong electric field will probably pull the ions out. But we believe that's not a problem, because most solutions, a few patented and that are actually already public patents, show that the key part of not having PID involves having a direct contact between the outermost part of your dielectric stack and the silicon, such that there is not a high electric field between the two.
Other questions? Okay. So let's thank Sebastian for great work.
Thank you.